Video I am going to discuss the electric field. When two charges are placed at a distance apart, they exert force on each other. Such a force is called action at a distance. Coulomb's law in electricity provides a method to find the magnitude of force between two point charges kept at a distance. It cannot explain the mechanism as to how two charges exert force on each other at a distance. The concept of electric field provides an explanation as how a charge can exert force on another charge kept at a distance from it. According to field concept, the force between two charges is a two-step process. In order to explain, consider that a charge small q is present at some point in space. In first step, it is assumed that the charge small q creates something called electric field in the space around it. Likewise, charge small q is called source charge. In the second step, it is assumed that when another charge q naught called test charge is placed in the electric field produced by the source charge q, the electric field exerts force on it. Thus, electric field due to a charge in the space around the charge in which any other charge is acted upon by an electrostatic force. Here it is important to understand the electric field of charge is the space property by virtue of which the charge modifies the space around itself. As a result, if any other charge is brought in the space around the charge, it experiences any force due to electric field produced by it. The electric field due to a source charge has its own existence and is present even if there is no test charge to experience the force. The significance of electric field lies in the fact that the space around the charge is important rather than the charge producing it. Further, the electric field takes finite time to propagate. If a charge is displaced from its position, the change in electric field at a distance small r will be noticed after a time small r by small c, where c is the speed of light. Now, electric field intensity. The electric field intensity at a point due to a source charge may be defined as the force experienced per unit positive test charge placed at that point without disturbing the source charge. The electric field intensity is also called strength of electric field or simply electric field. Consider that a positive test charge Q naught experiences a force capital F when placed at the observation point. F is a vector here, the point where electric field is to be determined. The electric field at the observation point is given by this equation. Above expression for electric field, it is assumed that when the test charge Q naught is placed at the observation point, it does not disturb the source charge. One way to ensure that test charge Q naught does not disturb the source charge is to keep its magnitude vanishingly small. If the test charge Q naught is not vanishingly small, it will disturb the source charge and hence electric field at the observation point will be different from the one had the source charge remained in the original position. Therefore, electric field intensity at a point due to a source charge may be defined as the force experienced per unit positive charge on a vanishingly small positive test charge placed at that point. If F vector is the force experienced by a positive test charge Q naught placed at the observation point, then electric field at that point is given by capital E is a vector here which is equal to limit Q tends to 0 capital F vector divided by Q naught. Idea of taking the limit Q naught tends to 0 is that on placing the test charge at the observation point, the source charge will not be disturbed. The electric field at a point is a vector quantity. From equation 1 and 2, it follows that unit of electric field in SI is Newton per Coulomb, that is N capital C capital minus 1. Force on a charge inside electric field, if capital E vector in electric field at a point, then by definition a charge Q placed at that point will experience a force which is capital F vector is given by capital F equals to Q into E. Now there is a problem related to this. Find the magnitude of electric field which will just balance a deuteron of mass 3.2 into 10 to the power minus 27 kg. Take G equals to 10 meter per second square. Now solution. Let E be the electric field that will balance the weight of the deuteron. Then small q E equals to mg. A deuteron is made of proton and a neutron. Therefore charge on deuteron q small q equals to 1.6 into 10 to the power minus 19 coulomb. Therefore E equals to m into small g divided by small q, that is equal to 3.2 into 10 to the power minus 29 kg into 10 to the power meter per second square divided by 1.6 into 10 to the power minus 19 coulomb, which equals to 2 into 10 to the power minus 7 Newton per Coulomb, that is vertically upwards. Now physical significance of electric field. The concept of electric field is of great significance. Two charges kept at a distance exert force on each other, which is termed as action at a distance. The concept of electric field helps us to understand the mechanism by which two charges kept at a distance exert force on each other. Further, as an alternative to Coulomb's law in electrostatics, it gives a method to find the force experienced by one charge due to the other in terms of the electric field produced by it. Electric field due to a point charge. Here I am giving you a figure to understand, which I will be giving you, make you understand later on. Let's first go for the figure. That a point charge plus q is placed at the origin O of the coordinate frame. Let P be the point where electric field due to the point charge plus q is to be determined. Let OP vector equals to R, small r vector with the position vector of the point P. To find electric field at a point P, place a vanishingly small positive test charge Q0 at point P. According to Coulomb's law, force on the test charge Q0 due to charge Q is given by vector F equals to 1 by 4 pi epsilon naught Q0 divided by R square into R unit vector, where R is a unit vector along OP. If E is the electric field at point P, then electric field vector equals to limit Q0 tends to 0 F vector divided by Q0 equals to limit Q0 tends to 0 multiplied by 1 by Q0 into 1 by 4 pi epsilon naught Q0 divided by R square into R position vector, unit vector, or E equals to 1 by 4 pi epsilon naught Q R square into unit vector R equals to 1 by 4 pi epsilon naught into Q divided by RQ R vector. So the magnitude of the electric field at a point P is given by E equals to 1 by 4 pi epsilon naught into Q divided by R square. Our expression for electric field, it follows that electric field is spherically symmetric as seen from the charge small q, and its magnitude decreases inversely as the square of the distance from the charge. Representation of electric field. Let us represent the electric field due to a positive charge by associating a vector in bracket in order to represent magnitude and direction, bracket closed. The magnitude and direction of the electric field at various points may be represented by arrows of suitable lengths. Points where the electric field has large magnitude, longer arrows may be used, and at the points where the field has small magnitude, smaller arrows may be used. To be accurately, the length of the arrows will vary inversely as the square of the distance of the observation point from the charge. Further, the arrows will point away from the charge in case it is a positive charge and will point into the charge in case it is a negative charge. According to this scheme, figure A represents the electric field due to a positive charge, and while figure B represents the electric charge due to a negative charge. Now, three components of electric field. Refer to figure 1. If x, y, z are the coordinates of point B, then position vector r equals to ix plus jy plus k, z I, j and k are unit vectors, and r equals to mod r unit vector equals to x square plus y square plus z square to the power half. This x square plus y square plus z square are in bracket. Putting position vector r and r in equation 4, we have electric field equals to 1 by 4 pi epsilon naught multiplied by q in numerator ix plus jy plus kz divided by x square plus y square plus z square to the power 3 by 2 in denominator. This is equation number 6. Therefore, the components of electric field in bracket magnitude only at point P along the three axes are given by Ex equals to 1 by 4 pi epsilon naught into Qx divided by x square plus y square plus z square to the power 3 by 2. Uy equals to 1 by 4 pi epsilon naught Qy divided by x square plus y square plus z square to the power 3 by 2. Ez equals to 1 by 4 pi epsilon naught Qz divided by x square plus y square plus z square to the power 3 by 2. Electric field in terms of position vector of source charge and the observation. Consider that the point charge Q is present at point A, whose position vector is OA equals to R dash, and the position vector of the observation point P is OP equals to R. See figure. A singly small positive test charge Q0 placed at point P experiences force due to charge Q, which is given by capital F equals to 1 by 4 pi epsilon naught into Q0 divided by AP square. That AP vector divided by AP equals to or F equals to 1 by 4 pi epsilon naught into Q0 divided by APQ into AP vector, that is equation number 7. AP is a vector from charge Q to the test charge Q0. From the figure, it follows that OA plus AP equals to OP, or AP equals to OP minus OA equals to R position vector minus R dash position vector. Therefore, the equation 7 becomes F equals to 1 by 4 pi epsilon naught Q0 divided by mod R minus R dash mod over Q into R minus R dash. Hence, the electric field at a point P is given by E equals to limit Q0 tends to 0, F divided by Q0 equals to limit Q0 tends to 0 multiplied by 1 by 4 pi epsilon naught into Q0 mod R minus R dash mod closed over that 3 to the power 3 into R minus R dash position vectors. These are now the equation, or E equals to 1 by 4 pi epsilon naught into Q divided by mod r position vector minus r dash position vector to power q into r position vector minus r dash position vector. This is equation number 8. Electric field due to a discrete distribution of charges. Electric field at a point due to a discrete distribution of charges can be found by making use of principle of superposition of electric fields. Principle of superposition of electric fields states that electric field at any point due to a group of charges is equal to a vector sum of electric fields produced by each charge individually at that point when all other charges are assumed to be absent. That n point charges q1, q2, q3 qn are distributed in space in a discrete manner. Suppose that we have to find electric field at point P due to the discrete distribution of charges. For this place a vanishingly small positive test charge q0 at the observation point P as shown in the figure. Suppose that the charges q1, q2, q3 qn exert forces f1, f2, f3 fn on test charges q0. If F1 is force due to the ith charge Qi on the test charges Q0, if I is force due to the ith charge Q1 on the test charge Q0, then F1 equals to 1 by 4 pi epsilon naught Qi Q0 divided by Ri square multiplied by Ri unit vector, where Ri is the distance of the test charge Q0 from the ith charge Qi and Ri unit vector from charge Qi to Q0. The electric field due to the ith charge Qi at the observation point P is given by EI equals to limit Q0 tends to 0 Fi divided by Q0 equals to limit Q0 tends to 0 multiplied by 1 by Q0 multiplied by 1 by 4 pi epsilon naught Q1 Q2 divided by Ri square into Ri position vector. This is equation number 9. Electric field Ei due to charge Qi at the observation point acts along the direction of the force on charge Qi. Likewise, the electric field Ei E1, E2 En due to the charges Q1, Q2 Qn act along the direction of forces on the test charge due to them as shown in the figure. If E is the electric field at point P due to the discrete distribution of charges, then by principle of superposition of electric fields, E equals to E1 plus E2 plus E3 plus plus En equals to integration sin I equals to 1 to n Ei. Question 9, we have E equals to integration sin I equals to 1 to n into 1 by 4 pi epsilon naught into Q1 divided by Ri square into unit vector Ri, or E equals to 1 by 4 pi epsilon naught I equals to 1 integration sin 2n Qi divided by Ri square into position vector Ri, which is equation number 10. Electric field in terms of position vectors of source charges and the observation point. Suppose that n point charges Q1, Q2, Q3 Qn are placed in space of the points whose position vectors are R1, R2 Rn respectively. Let Ri be the position vector of the ith charge Qi and R the positive vector of the observation point P in the figure. Earlier, the electric due to a point charge at an observation point in terms of position vector of the charge and the observation point is given by the equation 8. Using this equation, electric field due to charge Qi at the point P is given by Ei equals to 1 by 4 pi epsilon naught multiplied by Qi divided by R minus Ri to power Q into R minus Ri. Hence, electric field at a point P due to the discrete distribution of n point charges is given by E vector equals to I equals to 1 integration sign to power n to n till n into ei vector, or ei equals to 1 by 4 pi epsilon naught integration sign in which lower limit is I equals to 1 to n. Now qi divided by r minus ri to power 3 in mod, now into r position vector minus ri position vector, which is equation number 11. Electric field due to a continuous distribution of charges. Now we calculate electric field due to a continuous distribution of charges in the following cases. Number 1 is electric field due to a line charge distribution. Refer to figure in earlier chapter about this topic. Let E be the electric field at location R due to the line charge distribution L having linear charge density lambda. From the equation in this topic earlier discussed, the force on a vanishingly small test charge Q naught at location R position vector due to the large line charge distribution is given by F equals to 1 by 4 pi epsilon naught into Q naught, and integration sign in the lower limit is the L lambda dl means small l, now divided by mod R position vector minus R position vector R dash position vector to power Q into R minus R dash position vector. Here R is a position vector of the of the elementary position dl of the line charge L having charge lambda dl. Therefore, electric field at a location R due to a line charge distribution is given by E equals to limit Q naught tends to 0 F divided by Q naught, or E equals to 1 by 4 pi epsilon naught. Integration sign in the lower limit is the L lambda dl divided by mod R minus R dash to power Q into R minus R dash. This is equation number 12. Number 2, electric field due to a surface charge distribution. Here also refer the figure of surface charge distribution topic. Let E be the electric field at a location R due to surface charge distribution as having surface charge density sigma. From the equation in this topic, the force on vanishingly small test charge Q naught at location R due to a surface charge distribution S is given by F equals to 1 by 4 pi epsilon naught into Q naught. Integration sign in the lower limit is the S sigma ds mod R minus R dash to the power Q into R minus R dash. Here R is a position vector of the elementary portion ds of the surface charge distribution S having sigma ds. Therefore, electric field at location R position vector due to the surface charge distribution is given by electric field E equals to limit Q naught tends to 0 F divided by Q naught, or E equals to 1 by 4 pi epsilon naught. Integration sign in S lower limit into sigma ds divided by mod R minus R dash into R minus R dash. This is equation number 13. Number 3, electric field due to a volume charge distribution. Here also refer the figure of F due to volume charge distribution. Let E be electric field at location R due to a volume charge distribution, V having volume charge density rho. From the equation of F is this topic, F equals to 1 by 4 pi epsilon naught into Q naught. Integration sign in the lower limit is V rho ds mod divided by mod R minus R dash mod into to the power Q into R minus R dash. Here R dash is a position vector of the elementary portion dn of the volume charge distribution V having charge rho dV. Therefore, electric field at location R due to the volume of charge distribution is given by E equals to limit Q naught divided by 0, Q naught tends to 0, F divided by Q naught, or E equals to 1 by 4 pi epsilon naught. Integration sign lower limit is V rho dV divided by mod R minus R dash into R minus R dash. This is equation number 14. Earlier, as it was in force, Fe can be written as in this way. This is how big, so I am giving you directly a picture of it. Number 15. Electric field due to a circular loop of charge. Consider a circular loop of wire of negligible thickness having a radius small a. Suppose that the total charge small q is distributed uniformly over the circumference. Suppose that the loop is placed in yz plane such that its center coincides with the origin O as shown in the figure. Let P be the point at a distance small x from the center of the loop is to be determined. So first of all, go for the figure. Consider an elementary length AB of the loop of length small dl, then charge on the elementary length AB dq small q equals to small q divided by 2 pi a into dl. Let d be the electric field at point P due to charge dq on the elementary portion AB of the ring. Then magnitude of electric field at point P due to the elementary portion is given by d equals to small d equals to 1 by 4 pi epsilon naught into dq divided by cp square along cp. Now cp equals to x square plus a square divided to the power half. Now cp equals to x square plus a square to the power half. Substituting for dq and cp, we have d equals to 1 by 4 pi epsilon naught into q dl divided by 2 pi a multiplied by x square plus a square. These are in bracket. The electric field due to the elementary portion AB can be resolved into two components. First one, DEX along PX, that is along x-axis, and number two, DEN along normal axis to PX for the element AB. The components DEN will be along z-axis and in the downward direction. The components DEN of DE due to various elementary portions of the circular loop will not contribute to the electric field at point P due to the whole loop. It is because of the fact that the components DEN due to any two elementary portion of the loop located opposite to each other are equal and opposite and hence cancel out. In other words, net electric field at point P due to the whole loop of charge will be along x-axis. If DE makes angle theta with x-axis, then DEX equals to DE cos theta. In right angle triangle POC, angle OPC equals to theta. Therefore, cos theta equals to OP by PC equals to x by x square plus a square in bracket to the power half. As DEX equals to 1 by 4 pi epsilon naught into q dl divided by 2 pi a multiplied by x square plus a square into x divided by x square plus a square to the power half. Or DEX equals to 1 by 4 pi epsilon naught multiplied by qx dl divided by 2 pi a multiplied by here x square plus a square to the power 3 by 2. Electric field due to a whole of the circular loop is given by E equals to integration sign in lower one is total loop DEX equals to integration sign again total loop 1 by 4 pi epsilon naught qx dl divided by 2 pi a multiplied by here 2 pi a is multiplied by x square plus a square to the power 3 by 2 equals to 1 by 4 pi epsilon naught into qx divided by x square plus a square to the power 3 by 2 along px. This is equation number 16. Special cases. Let us evaluate the electric field due to the circular loop of the charge in the following cases. Number 1, when point P lies at center of the loop, in such a case x equal to 0, then from the equation 6 it follows that E equals to 0. 2, when point P lies at a distance x greater than a, in such a case in the equation 16 a square can be neglected in comparison to x square, then E equals to 1 by 4 pi epsilon naught into q divided by x square along px. It is also the expression for electric field due to a point charge q at a distance x from it. Therefore, a circular loop of charge behaves as a point charge in case the observation point on its axis is at a distance quite large as compared to the dimension. Now here is a note: the electric fields due to a circular loop of charge and a point charge are identical provided the distance of the observation point from the circular loop is quite large as compared to its radius of the loop.